Good morning, and thank you for tuning in. I am Frank Willmore. I'm an HPC engineer with the Department of Research Computing at Boise State University. And today I'll be speaking about software stewardship for research software in the context of a set of codes I work on called vacuums. I'm the lead software administrator at Boise State University's Research Computing Department, and I'm also the software administrator for C3+3 Consortium's Falcon supercomputer, which was gifted to us from Idaho National Laboratory. And in addition, I'm the principal developer of Vacuums, which is a collection of research codes used for analyzing free space in materials, which was developed largely during my PhD in chemical engineering at the University of Texas. Continued on while working as an NRC postdoc at NIST, and here and there I've continued to work on it. This is the team of folks I work with. All great work requires a great team, and I have the good fortune of working with an excellent group of folks at Boise State. A point that I would like to drive home today is that student-developed research software matters. Codes that are developed during the course of graduate work can also become very important research infrastructure. Some examples of this include the popular molecular dynamics package HUMD, which was originally developed as part of Joshua Anderson's graduate work at the University of Iowa. Another example is the low-level virtual machine developed at the University of Illinois during graduate work, and which has become the foundation for Apple's Clang compiler, as well as NVIDIA's NVCC compiler, and also now Intel's OneAPI compilers. These are all now based on LLVM. And perhaps your work may be the next great contribution, may be something significant. Point being that maintaining software beyond the research published graduate cycle is a known obstacle to the reproducibility of results. PIs should work closely with their teams and with their research computing team at their universities to develop a stability strategy for their software and to include that strategy in proposals. It was asked to install recently, which is this fast structure. It's a genetics piece of software program. And it looks to have been developed during the course of graduate work and then later not maintained. So to share a couple things about it, it looks like it's in pretty good shape. It's in source control. It has tagged releases. You see version numbers here. It has a nice README. It has directions. So it looks in pretty good shape, except that it hasn't been maintained. It's 8 years since last updates were added to it, which is a shame because it appears to be again, I was asked to install the software, and it appears to be a software which is in use. As we see, it has 11 watchers, 50 people have forked it, and 114 people have started the repository. So people are paying attention to it. So what I want to say, though, is that it seems like development was good, and then it seems like there wasn't a plan to maintain it. Notably, this is a code that was written in Python 2, which has been end-of-lifed, and it's not recommended that anyone run Python 2 anymore for anything. It's not maintained. There's outstanding issues with it, and everything has moved to Python 3. And in fact, there was a pull request submitted to this to the repository for this, making updates to support Python 3. And we can see from dialog here, this was submitted in 2015. And we see the original developer saying, thanks for taking time to make these updates. I'll make sure to look it over and merge it as soon as possible. And then there's no motion on it since 2015. We do see comments coming in afterward, 2018, 2019, asking, is there any movement on this? 2020, a year later, it's been a while since this was first posted. Four people basically also chiming in to say that they would like to see this integrated and to be able to continue using the software. And it hasn't happened. And so this is what we would like to say, that it's important to have a plan for sustainability so that things don't end up like this. There are tools that can help. Source control. This should be a no-brainer, even for things like scripts and workflows. I even put recipes in source control. I'm just kind of a geek that way. It's got well-understood interfaces, with Git being fairly ubiquitous as a tool for source control. It allows for an auditable record of work that's been done. It's a recipe for reproducibility. You can get to the same point again. And even if you think your code is poor quality or you don't feel confident in it, putting it into source control and exposing it to review means you're going to provide opportunities to improve it. Versioning. Version number is a control variable. This is a soapbox I have, that Scientific method relies on control variables, and version number is a control variable, a snapshot in time of what the software looked like and how it was built and how it operates. Semantic versioning is a well understood model of versioning where you have a major version where you changing major version means you're introducing incompatible API changes, a minor version, which is where you're adding new but yet compatible functionality, and a patch version, which is just bug fixes and everything still remains compatible. Besides semantic versionings, there are also other versioning models that are still in play. For example, the stable, unstable, even odd number versioning, which was originally developed for Linux kernel, is still in play and still used by the HDF group for HDF5. Another one is release date. LAMPS is still versioned by the dates of its release. User-facing documentation and examples. There's a well-understood way of publishing your documentation using something called Sphinx or Read the Docs documentation. Writing things in Markdown. Markdown is the currency for GitHub as well as many other parts of the web. Having a build system or a build system generator. Most commonly, this is AutoTools, or now more so CMake is the generator for a build system, which makes it easier for a admin or another user to install a piece of software to their system. And it's important to remember here is that if no one can build your software, then no one can use it. And if no one understands how to run your software, no one can use it. And if no one can use your software, it's lost. It dies. Some other important tools include software packagers and installers. For example, RPM-based packagers are Yum, apt, Zipper, etc., and Debian packages. These are de facto standard for system administrators, and this is how most system software is distributed. Another option is Homebrew, it's developed specifically for Mac OS, and SPAC, which was actually modeled after Homebrew, but it's targeted for high-performance computing systems. It's highly extensible with packaging workflows that are written in Python. The downside to SPAC is that it has a fairly steep learning curve. SPAC is the tool that I chose to package vacuums. So Vacuum's most accessible code is a implementation of the cavity energetic sizing algorithm, which allows sizing of cavities in permeable polymers. I've added a number of Monte Carlo methods for sizing the volumes of and surface area of overlapping groups of cavities, as well as extended Whittam insertions to calculate gas solubilities of the polymer. There's also a molecular dynamics code, a probabilistic molecular dynamics code, works well, but only for materials with extremely high free volume. There's a number of rattle techniques for spheres and other hard particles, just to show what space is available to motion for particles. And I've continued adding different utilities and extending ability to generate code as inputs for ray tracing with the ray tracing program PavRay. So let's look at some of those. For example, the cavity sizing. This is a polystyrene sample where I've looking at a number of cavities of a given size for the sample. This is a sample showing cavities as the gray bubbles, and including isosurface of insertion energy for the free volume via Whittam insertion. So you can see how those overlap nicely. This is a three-dimensional TIFF file just showing the insertion energy versus position within a sample. This is an attempt to grab several measures at once. The red showing Leonard-Jones fluid molecules, gray cavities, and then again the green showing this isosurface of the free energy. These are rattle volumes for that same Leonard-Jones fluid, and these are showing where the space available if you were to wiggle each of the atoms individually within that sample. This is again trying to show many measures at the same time. We have Voronoi cells here, along with cavity dynamic, just polymer evolving over time. We see dynamic cavities, and we also see the free volume isosurface changing over time. And finally, this one is showing hard particle free rattle volumes for hard particles. This is built as an extension to whomd. So there were some fun things in here that I put together, and taking this as a starting point, I had a number of these codes that I had interest in, but there was not adoption or use, and there was some notoriety for the ability to render pretty pictures and video. I had a reputation for making some of these drawings, and I had a DOI and a Git repo since 2012, but no instructions, no examples, and just a disparate set of make files for building it. No dependency management, and it was largely an abandoned project, save for a handful of sprints over the course of maybe 15 years of development. Now, to find a path forward, I've worked to locate as many of the working codes as I could find and salvage them from tarballs, from things where I had just archived versions of them in different configurations. I'd done a lot of this work before source control was quite so ubiquitous, and then tried to curate and weed out as many codes that either weren't working, didn't make sense anymore, to clear redundancies and files with suffixes like the old version, the previous version of something. Just the stuff that you see when you're going through an old project, and find the salvageable but incomplete codes and to try to turn them into something useful, or to list them as apocryphal. And so I've sorted codes into logical categories of libraries, applications, and utilities because that's what made sense for this project. I developed a coherent build system for each of the categories by identifying the patterns in the slew of make files which I had there, and I chose to factor those using CMake as a build system generator. And I developed a top-level CMake lists.txt file which integrates all these libraries, applications, and utilities and manages their dependencies. Plus it adds hooks for specifying different build options more elegantly once all the configuration is done. So we now have a cross-platform build system which opened the door to porting this code to additional platforms, different architectures, and different compilers. Originally it built only on Linux x86, and now it also builds on ARM, as well as Mac OS x86 and Mac OS ARM. So I can run it on my new M1. All these codes now run on my new Mac M1. And I've been able to extend to new platforms means fixing some of the bad design patterns and revealing bugs. Some of the codes no longer compiled with modern compilers or didn't obey the rules for Clang, and now they do. So SPAC was chosen as a vehicle for packaging primarily because of my familiarity with it, as I've been working with it for the past several years. But it also allows for the automatic building of dependencies, which is very important. Your software, it depends on other pieces of software, and SPAC will build those for you. RPMs would have been appropriate, but it meant shipping compiled codes may not take advantage of, for example, AVX vector instructions, which would make codes run faster. And it's also possible to ship ready to build tarballs, but that requires a lot more work on behalf of the system administrators. And I like to say show, don't tell, which in this case means adding examples as well as instructions. So here's my CMake lists.txt file. It shows the ways that it's pulling in the different requirements for X11, for CUDA, for TIFF library, and how it's putting all these together, adding the subdirectories in there, and making sure that everything's in there to build the software. And here is my SPAC package for the code. It shows the TIFF and CUDA variants where you can build without the TIFF library if you don't need it, and you can build without CUDA if you're going to be running on a non-GPU system. Some of the utilities require CUDA. The free volume index utility requires CUDA to run. And then this is also showing for different versions of the software, and then also you're declaring your different dependencies. This is SPAC's way of getting everything in order for you. And this is it. This is the entire packaging file for this software. Part of the reworked vacuums, the modern vacuums, which is the ability to generate 3D images of free volume as TIFF images, which can be easily imported into a visualization program such as PairView, which we see here. And so this is our high resolution model for polystyrene with 60,000 atoms. We see the black spaces here, and some level of continuity of those is visible, representing paths through the material for diffusion. And you can also throw this up as an isosurface as well, which is similar to some of the hulls types of representations you've seen before. So again, we have another way in ParaView to look at the free volume using the same data set and the same TIFF file that we generated from vacuums. The GitHub site for vacuums, notice it now has a README, citation information, installation instructions, as well as user and developer guides describing the I/O formats in play, an applications user guide for the pieces within it, similarly for utilities, and also a developer guide, plus a roadmap for what's planned for the software, and release notes for as things are updated and released for use. It's just notes on what's available and what's different. And as well as, and probably perhaps the most important, is that there's now an example for running workflows using polystyrene, generating statistics, and also sample scripts for doing the work. So we come to the so there's the README showing just the results, but then there's also the scripts themselves in the original file. So this is how everything was generated. You can see step by step. So Vacuums is updated and re-released, and we have our first citation. This is exciting because it's coming to fruition after many years of work. We would like to acknowledge the many parties which have helped sponsor some of this work along the way over the course of many years, as well as to name a few individual contributors, in particularly Janani Sampath, who had offered the polystyrene configurations. And with that, we'd like to open it up for questions. Thank you.